everybody. In this video, we're going to talk about section 7.1 from our textbook, which is solving inequalities in two variables. So first, we're going to remind ourselves how to solve just an inequality in one variable. And bear with me as I get used to this new tablet that I got to record these videos. So we're going to solve the inequality and we want to solve for x. So first, distribute the 2 as we go to it. So 2x minus 2 less than 6. And then we want to isolate the x. So go ahead and add 2 to both sides. And so I have 2x is less than 6. Try to be careful not to switch your inequality to an equals. Sometimes when we say we treat this like equations, we're kind of tempted to do that, but don't change your inequality to an equals. So the 2's cancel and I have x is less than 3. And so from here, we can write it as in interval notation and we can write it via number line. So I'm going to draw the number line first. And I'm going to put 3 on the number line. You don't have to put 0 in there. You don't have to do anything except put the 3. And this is x is strictly less than 3. It doesn't have the equals there, so we are not going to include 3. So that means if I put a circle around it, it's going to be open because I'm not including it. And then it says that x is less than 3. So if x is less than 3, that means that we are going to shade to the left of 3. Right? If you're smaller than 3, you are to the left of 3. So we are going to shade over here. So that is our solution. In interval notation, then I'm going to say x is in the interval minus infinity all the way to 3, but I don't want to include 3, so it becomes a parenthesis. Okay, so that is with one variable. So notice that this was essentially, I was graphing the x's here. So in this section, in section 7.1, we're going to be graphing inequalities in two variables, or solving inequalities when you have two variables. So my first example is going to be solve x plus y less than 6. So graph the solution set is what this means. So x plus y less than 6. And what we're going to want to get to is to do a system of inequalities, for solving this. So notice that when I had it in the first example with just one variable, x, we drew a number line to plot our x. So now I have two variables, x and y. So that means I need two number lines to plot my x and my y. So then this is where it's going to look like the Cartesian coordinate plane. So I'm going to have my x and my y. And so we're going to use the Cartesian plane to draw the solution for this. So the first thing is to draw what this equation will be if it was equals, if what this expression will be, if it was equals. So if it was equals, you will have an x-intercept by setting y equal to 0. So you will have x is 6. So at x equals 6, you will have an x-intercept. And same thing to find the y-intercept. We let x equal 0. And when x is 0, we get y equals 6 also. You could also put in y equals mx plus b and solve. Now this is, again, as before, it doesn't have an equal, so I don't want to include the points on this line. So I'm not going to draw a solid line because I don't want to include the points on this line. So we're just going to go and I'm going to draw a dotted line because I do not want to include the points on this line are not solutions to the inequality. And now we're going to shade the solution set. And so sometimes it's helpful to put it in mx plus b form. So move the x to the other side. So it'll be negative x plus 6, right? And I could have done this also to graph it. Y-intercept is 6, slope is minus 1. So you go to 6 and go 1 down over 1 down over 1 until you get the line. But writing it in mx plus b form helps me decide which way to shade, because now I know that y is less than the points on the line, on the dotted line. So all the y values that are smaller than that will then be on this side of the line. Had I said y greater than, then all the y values will be above the line. So this will be this is the graph of the solution. Of the solution set. Notice that here I cannot really write it in interval notation like I did in the previous example here. We can't really write it like that because we have the two variables. So our solution set is going to have to be a graph. So let's try another one. So another example, let's call it example 2, is going to be graph the solution set. And your book calls it the feasible solution, which is the same thing, graphing the solution set. Graph the feasible solution to the inequality. Let's say 3x minus 4y greater than or equal to 12. And so think about how you will do that. And in this one, I'm going to show you another way that we can graph the solution set. So the first thing is graph the line, the points on the line. So I have two variables, so I'm going to need my xy coordinate plane. And so I need to find the points on the line. So same thing, you can either find your x and y intercept, or you can put it in mx plus b form. So I'm going to do it both ways. So first, by doing x and y intercepts. And then we'll do it by mx plus b. So by x and y intercepts, so let's find the x-intercept first. So we let y equal 0. So when y is 0, what's x? Plug in 0 for y, so you get 3x. 3x is greater or equal to 12, which means x. In this case, I actually want to find the equals, so it's going to be x is equal to 4. So that's my x-intercept. And for the y-intercept, we let x be 0. And we're going to get y is equal to, so when x is 0, that's 0. So you get negative 4y equals 12. So y will be negative 3. So we're going to be down here at negative 3. And now I'm going to sketch the line. But before I sketch it, I want to ask myself, am I including the points on the line? So is it going to be a solid line? Or am I not including the points on the line? And is it going to be a dotted line like the previous example? So I go to my inequality for that, and I notice that it does have the equals. So that means that it's going to be a solid line. The points on this line are going to be included. And so now I want to see, well, which side do I shade? Do I shade above the line, or do I shade below the line? And when I do the x and y intercept way, I could pick a test point to check. And a really nice test point to pick is 0, 0, only if your line doesn't go through 0, 0. So you want to pick a point not on the line. So your test point is a point not on the line. So I'm going to pick 0, 0 because working with 0 is nice. So if I pick 0, 0, I get 3 times 0 minus 4 times 0 greater than or equal to 12. And I'm going to ask myself, is this true or false? So 3 times 0 is 0, minus 0 is 0. Is 0 greater than or equal to 12? And this is false. So that means that 0 is not in the solution set. So 0 is here. So that's where 0, 0 is. So 0, 0 is not in the solution set, so that means that this side can't possibly be the solution set. So the solution set is the other side. So that's my solution. So this was one way of doing it. Right? The other way is by doing mx plus b. So let me show you how to do that one. So by mx plus b. Notice I'm being careful to not say y equals mx plus b because we don't have an equation. So I'm just saying by mx plus b. So my inequality was 3x minus 4y greater or equal to 12. And I want to put it in mx plus b form. So that means I want the x and the b on the same side. So I'm going to move the 3x. So minus 3x minus 3x. So I'm going to have negative 4y is greater or equal to, you always want to write things in descending order, so I'm going to write the minus 3x first from degree. That's what I mean by descending order. So this is degree 1, x to the 1, and that has no variable, so it's degree 0. And now we want to get the y all by itself, so I'm going to divide by negative 4. Whoops. So when I divide by negative 4, everything, both sides, so that means every term. Now I'm going to have, and here we have to be careful, right? Because what happens when you divide by a negative? I'm going to have y, and then negative divided by negative becomes positive, so I have 3/4 x minus 1/4. But when you divide by a negative, the inequality switches. So y is less than or equal to. And now I could use this to graph my equation. Oh, sorry, that should be a 12, which means this is really negative 12 divided by 4, and negative 12 divided by, or 12 divided by negative 4 is negative 3. Okay, that makes more sense. So our y-intercept is negative 3. So I'm going to go to negative 3, and my slope is positive 3 over 4. So that means I'm going to go up 3 and over 4. So it puts me over there, and now I can draw the line. Same thing, it has an equals, so that means I get to include the points on the line, so I would draw it solid. Whoops, my line didn't quite connect there. So that's the line. Now when you do it in mx plus b form, the nice thing about it is that now the way that the symbol is pointing, it lets me know which side of the line to shade. Y is less than the points on the line. So I'm looking at the y values, so the y-axis, so I have to be less than, so below the line. So this means we want the points below the points on the line. So I'm going to be shading over here, below the line. So it's the same answer as that we got up here. Now the one thing about this is that you have to remember that anytime you divide by a negative, divide or multiply by a negative, then you have to flip the inequality symbol. So that's really, really important. And I'm not going to make you do one or method or the other. It's just personal preference. I like the finding my x and y intercepts and then graphing it that way. But it just kind of depends on the equation too. Sometimes mx plus b just works out nice. Okay, and one more example of this, and then I'm going to start a new video because this might be running too long for YouTube. So another example is graph the solution to the inequality in two variables. And the inequality is x less than 3. So how do we graph that? And some of you might be thinking, wait a minute, why did she write in two variables and there's only one variable? Well, because that means that we want to make sure that we graph this in the Cartesian coordinate plane. So even though you only have one variable, when we're told that this is an inequality in two variables, that means that we need to graph it in the Cartesian plane. Just because the y is missing, that doesn't mean that the y doesn't get graphed. So we're going to graph it. When you see this in two variables, that means that you're graphing it in the xy plane. So x is less than 3. So to review, if it was just x equals to 3, how would you graph that, right? So if x was equal to 3, this is a what kind of line? Horizontal or vertical? Essentially, it's fixed at when x is 3, y can be anything it wants. So we get a vertical line. If it was y equals 3, then you have a horizontal line at 3. Right? A line like this, a vertical line, has undefined slope because it has a rise, but it doesn't have a run. So that's what x equals 3 looks like. So now going back to the inequality, x less than 3. So that just means that we want to graph all the x's that are less than 3. But this is an inequality in two variables. Now y can be anything it wants as long as the x is less than 3. So we're going to go over here to 3 and we're going to graph this same line, but notice that I don't have the equals. So x is strictly less than. So that means that the points on this vertical line are not included. So it's a dotted line. And the solution set is all the points x, y that are less for where x is less than 3. So it's just going to be all this, the left side of x. Kind of like when we started with the first example here, right? X, it ended up really being that x was less than 3, but this was an inequality in a single variable. And so we were expected to only graph it in a single number line. But for the next example, we are told that this is an inequality in two variables. So we don't only graph the x's, but we also have to graph the y's that go with it. So this will be the solution. Okay, I'm going to record another video, part 2, with doing a system of equations.